In this video, we are starting chapter 9, which is about solutions. So up above, I have a beaker with what looks like water in it. However, there's also some salt dissolved in that water. And off to the side, we can see that there are H2O molecules, and they're sort of pulling apart this ionic compound here. So the water molecules are surrounding pieces of that ionic compound. So we'll talk more about this later, but this is what makes up a solution. We have something that is dissolving something else. So if you watch any of the medical dramas on TV like Grey's Anatomy, you may have heard a doctor call for an intravenous solution or an IV solution. So there's one type of IV solution called a normal saline solution, and this is made up of 9 grams of sodium chloride dissolved in 1 liter of solution. So this is what we call a concentration. And solutions are always going to be made up of 2 things or more. So physicians can actually select from a range of IV solutions that are based on a patient's needs. So when we're looking at a solution, it's really just another name for a homogeneous mixture, which we learned about a long time ago. So we can't see the individual components of the mixture. They're mixed really, really well. Now, the major component of a solution is called the solvent. So this is typically going to be the same phase as the solution itself. So for example, if you have a liquid solution, the major component will also be a liquid. Now, each minor component of a solution, and there can be more than one, is called the solute. So a lot of S words in this chapter. We have solution, solvent, and solute. So if we go back to the first slide, in this case, water is going to be the solvent. It's going to be present in a larger amount. And the solute is the ionic compound. So this could be sodium chloride, for example. I also have some other examples down below of different types of solutions. So in the table, we have our solvent in the first column and the solute in the second column. And we're just going to talk about the phase of the solvent and the solute. So just as an example, we know that the air around us is made up of multiple components. There's nitrogen gas, oxygen gas, carbon dioxide, etc. And the largest component is nitrogen gas. It's about 78% of air. So that would be our solvent. And then our solutes would be everything else that's in air. So O2, CO2, etc. Now, in some cases, we could have different phases in our solution. So for example, if we think about carbonated beverages, so maybe you like fizzy soda. The liquid is most likely water, and that will be our solvent. And then the gas that's in the solution is going to be considered a solute because it's present in a smaller amount than the solvent. So typically in carbonated beverages, the gas is CO2. And then we could keep going. For example, alcoholic beverages are composed of ethanol in water. So water would be the solvent. It's present in a larger amount, hopefully. And then ethanol is the solute. And then down below, we actually have dental fillings that might contain something like mercury or whatever alloy it's made of. So there's all sorts of different solutions that we can make. Now, what causes a solution to form? So the simple answer is that the solvent and the solute have to have similar intermolecular interactions. So the simple rule here is like dissolves like. So solvents that are very polar, like water, will dissolve solutes that are very polar, or even ionic. So we can dissolve salt in water as well. Solvents that are nonpolar will dissolve nonpolar solutes. All right, so down below I have that same picture that was on the first slide. And again, we know water is polar. We have that electronegativity difference between hydrogen and oxygen. And the shape of the molecule also helps with that polarity. Now let's say the ionic compound here is sodium chloride. So we have alternating sodium and chloride ions. And the water molecules are going to surround those ions and pull them off of the crystal. So let's do a practice problem. Let's determine if water, which is polar, will dissolve the following molecules. So our first molecule is called methanol. And if we draw the structure of this molecule, it looks like that. So we know that oxygen is very electronegative, and it's more electronegative than carbon and hydrogen. So we're actually going to see electrons moving up towards oxygen, and we're going to get an overall dipole moment kind of through that oxygen. So this is definitely a polar molecule. So we can say that water will dissolve that molecule. So methanol is also known as wood alcohol, and in the 1920s, I believe, the United States went through a period called Prohibition, where alcohol was outlawed. So many people actually made their own alcohol called moonshine, but one problem with that is sometimes instead of ethanol, which is what's normally in an alcoholic beverage, they would get methanol. And methanol can actually cause blindness if you drink too much of it. So there were a lot of issues with the fact that alcohol was illegal, so people were making their own alcohol and not properly purifying it. So, you always got to be careful and know your chemistry, right? Okay, let's look at number 2, Br2. Okay, so is this a polar or non-polar molecule? So we have two of the same atom bonded together. So we actually don't need to really think about electronegativity here because the two atoms have the same electronegativity. So they're going to equally share electrons, which means that it is nonpolar. So water will not dissolve this molecule, right? Because it's not polar. All right, let's look at the last one, potassium chloride. So we have a metal, potassium, and a nonmetal, chlorine. So what type of bond do we expect a metal and a nonmetal to have? Ionic, right? If you have a metal and a nonmetal bonded together, they're going to completely transfer electrons between each other, so that will give us an ionic bond. And earlier we said that water will dissolve ionic compounds. All right. So let's do another practice problem. So let's determine if benzene, which is C6H6, will dissolve the following. So benzene is actually a non-polar molecule. So remember, like dissolves like. Benzene, as a non-polar molecule, will only dissolve other non-polar molecules. So go through the following molecules and see if you can figure out whether benzene will dissolve them or not. And just a quick hint on number 2. Number 2 only has carbons and hydrogens, just like benzene. So those might be similar. So pause the video, see if you can figure this out first, and then we'll go over it together. Okay, so let's look at the first molecule. Again, it looks like we have a metal and a nonmetal bonded together. So on the last slide, we saw that if you have a metal and a nonmetal in a compound, that will be an ionic compound. So will benzene dissolve an ionic compound? No. So let's see. Benzene will not dissolve MgCl2 because benzene is nonpolar and magnesium chloride is ionic. What about number 2? Do we think that this will be polar or nonpolar? So again, this looks kind of similar to benzene. It only has carbons and hydrogens. So this is going to be nonpolar as well. So will benzene dissolve C6H14? Yes. All right, and then let's look at HCl. So this time we might need electronegativity values. Okay, so hydrogen has a value of 2.1, chlorine is 3.0. So the difference between those values is 0.9. So is that considered a polar molecule or a nonpolar molecule? Polar. So will benzene dissolve HCl? No, since benzene is nonpolar, it will not dissolve HCl. Okay. Now that brings us to a couple of terms that we might use throughout this chapter, soluble versus insoluble. So we use the word soluble to describe a solute that dissolves in a particular solvent. So for example, we said earlier that sodium chloride dissolves in water. So we would say that NaCl is soluble in water. And then we use the word insoluble for a solute that does not dissolve in a solvent. So we said earlier that Br2 does not dissolve in water. So Br2 is insoluble in water. Now, another example, down below we have a picture of water and oil. So oil is nonpolar and it will not mix with water, which is polar. So if you've ever noticed that before, that separation of oil and water, that's why they don't mix. One is polar and one is nonpolar. But up above, I have some iced tea or maybe hot tea, either way. And sugar is polar, and therefore it can dissolve in water. Now, a couple of other terms you might see are miscible and immiscible. And these sort of mean the same things as soluble and insoluble. So if the solute and the solvent are both liquids and soluble in any proportion, we use the word miscible, and then the word immiscible if they are not. So what does that mean? So sometimes solutes will only dissolve in a solvent up to a certain point or in a certain amount. But sometimes they can dissolve in any amount. But we might not use those terms miscible and immiscible as often. However, that does bring us to the term solubility. So there's usually a limit to how much solute will dissolve in a given amount of solvent. And this limit is called the solubility. So for example, let's say you're trying to mix sugar in cold tea. So maybe you're having a cup of iced tea or a glass of iced tea, and you're trying to put sugar in it. It's kind of hard to dissolve sugar in cold water. You might be able to dissolve a little bit, but a lot of it's just going to stay undissolved, right? So that would be the solubility of the sugar at colder temperatures. But let's say you heat up the liquid. So let's say you have a hot cup of tea and you add sugar. It dissolves really easily. So that would also be the solubility of sugar. And the solubility is clearly temperature dependent. So some solutes have a very small solubility, while other solutes are soluble in all proportions. And again, solubilities will vary with temperature. So looking down below, we have a list of solubility values. And the units for this are grams in 100 milliliters of water. So, for example, sodium chloride, we said was soluble in water. So we can dissolve 36 grams of NaCl in 100 milliliters of water. But if we try to add more sodium chloride to that 100 milliliters of water, it's probably not going to dissolve anymore. So we might just see some leftover sodium chloride sitting at the bottom. Now, sugar is also soluble in water, so we can dissolve 120 grams of sugar in 100 milliliters of water. Now, if we look at some of these gases up above, notice that their values are really small. So CO2, which is in carbonated beverages, its solubility is only 0.15 grams in 100 milliliters of water. Now remember, CO2 is a gas, and gases want to be out in the atmosphere, right? They don't want to be confined to a space. They want to move around. So it makes sense why it's really hard to dissolve a gas in a liquid. In fact, if you've ever used one of those machines to add carbonation to your beverage, you really have to apply pressure to get a gas to go into a liquid or to dissolve a gas in a liquid. So the solubility of gases is usually pretty low. Okay, now one last term is saturation. So if a solution contains so much solute that we reach its solubility limit, the solution is said to be saturated. Now, if a solution contains less than the solubility limit, it is unsaturated. But then there's special circumstances where more solute could be dissolved even after the solubility limit is reached. And these very special solutions are called supersaturated. And they are actually not very stable. So if our solute is a solid, it can actually recrystallize in solution if there's a supersaturated solution. So let's watch an example of that. And we just added an extra little crystal of solute. And notice that it's now causing other particles to crystallize. That's pretty cool. We can create supersaturated. All right. So I think we'll stop there for this video. In the next video, we're going to talk about different types of concentrations. So how can we express the amount of solute in a certain amount of solvent? So I will see you then.